of 10 years is divided equally between them, and each of them gets -5, the value. Each of these cells, you see two entries. The first one is the value of the first agent, the blue agent, and the second one is the value of the second agent. Okay. Now, what happens is, of course, if both of them cooperate, this is the best possible scenario. But what will happen is, now they are being interrogated in two different rooms, and this agent has no idea what the other agent is doing. The other agent could be cooperating or defecting. Okay. Now let's see. If this guy cooperates, now initially let's say they decided to cooperate. Okay. This is fine, but what will happen here is, just hang on, I might have made a little mistake here. These of them, each of them should be -1 and -1, not 1 and 1. -1 and -1. Okay. So when both of them are -1 and -1, what the blue agent will see is he's getting -1 is his reward here. But if he chooses to go to defect, his reward is 0. And 0 is more than -1. So what he'll do is unilaterally, the keyword here is unilaterally, he will defect. Okay, so from -1, he goes to 0. Now again, so what happened? Yeah. Now, conversely, if again we are starting from here, which is the best possible scenario for both of them, if this guy is cooperating, and the red agent suddenly decides that, okay, I get -1 here, but if I choose to change my action from cooperate to defect, I'll get 0. And so the red agent then defects, and so he gets 0. But the other guy suffers from -1, now his value is -10. Okay, so the key here is unilaterally changing actions, not together, but unilaterally. Now from here, let's look at one of these cells. Suppose they're here. So this person is defecting, this person is cooperating. Cooperate, what's he getting? -10, right? But if he switches his action to defect, he'll get -5. Likewise, if we're here, and this person is cooperating, this person is defecting, so when this person is cooperating, he's getting -10 is his value, the reward, and then if he switches his action from cooperation to defection, then his value goes from -10 to -5. So that's an increase of 5, right? And so unilaterally, again, the second agent will defect. In fact, this is the Nash equilibrium, -5 and -5. Both of them will defect. Although this is the best possible set of actions for both of them, they're not coordinating. Okay, there's no secret communication between them because they're being interrogated in two separate rooms. The Nash equilibrium is when both of them will defect. Okay, and this is what happens in real life too. So this is one example of Nash equilibrium. Here is another example of Nash equilibrium. There are two birds, and there is some prey. Okay, now they can either there are two possible actions. They can play dove or they can play hawk. Hawk is aggressive and dove is docile. Now what happens if both of them play dove? Both of them are docile, and so they will share the prey, and each of them gets a value of, so if both of them take this action, dove, then they will share 5 and 5. The total value is 10, shared equally, so it's 5 and 5. Okay. Now, if one, let's say the blue player chooses hawk, okay, he'll be aggressive, and but this other player, I'll use for this. This is game theory, so I'll use the word agent and player interchangeably. Excuse me for using the word player occasionally instead of agent. Anyway, so this is agent 2 or player 2. This agent is playing dove, okay, and this agent decides to, instead of playing dove, he'll play hawk. He'll be aggressive. So he'll aggressively take the prey. So he gets the full prey, prey, the hawk, and this person gets nothing. So 10 and 0 are the rewards. Okay. Likewise, if this player plays dove and the other player plays hawk, then they share it this way, 0 and 10. The person who's playing dove gets nothing, the person who's playing hawk gets 10. Now, what happens is, if both of them play hawk, then there'll be a fight, right? And because of the fight, there will be some loss of energy. And so ultimately, they'll have to share the prey. But it's not 5 and 5 because you have to, because of the energy expended, you have to take away 2 from each. And so the reward for each of them is 3 and 3. Now, let's see what happens. Of course, what's best for them is both playing dove simultaneously. Now, let's look at each player's perspective separately. Now, let's say we are here. Both of them by default are playing dove. This blue agent will think, okay, I'm getting 5. But if I switch my action to hawk from dove, what will happen? This guy is playing dove. If I switch from dove to hawk, from 5, my value will change to 10, right? So he has an incentive to switch his action from dove to hawk. Likewise, it's the same thing for the other player. Now, let's say this player is playing dove, and so we are here, and this player sees that, okay, if he plays dove, he's going to get 5. He doesn't care what the other guy is getting, right? He only looks at 5. But if he switches his action to hawk, he will get 10. And so he will switch his action to hawk unilaterally. But you can analyze that this is an action. Now, what happens from here? Let's say this scenario. This person is playing dove, and this person is playing hawk. Okay, he is getting 10. What will this guy think? This agent will think that, okay, he's getting 0, but if he switches his action to hawk, he will get from 0 to 3. Okay, so this person will change his action from dove to hawk. And likewise, if we start from here, this person will change from dove to hawk too. So ultimately, from here, there is no deviation. This is the Nash equilibrium. So what happens if the red player moves from hawk to dove? From 3, he's getting 0, right? So there's a net reduction in his value. So this player or this agent has no incentive to switch his action from hawk to dove once they're here. Likewise, if look at the blue agent here, the blue agent is getting 3 when playing hawk. But if he were to switch his action from hawk to dove, what will happen to the value that he's getting? From 3, it goes down to 0. So again, the blue agent doesn't have any incentive. So both the players are trapped in Nash equilibrium, which is 3, 3. Both of them have to play hawk, although the situation warrants that dove and dove is the optimal pair of actions. Since each of them is acting unilaterally, this is the equilibrium point. That's the Nash equilibrium. You had a question. I just created this as an example. No.
One more thing is, sir, by hawk and dove, 3 and 3 you have given, sir. So can we make it minimized until till that energy will be recouped? Till the 5 and 5 should come in the second row.
Let's not worry about all the details.
Okay.
It's just a very simple example. I could have made it 4 and 4, 2 and 2. There are so many ways to plug in all these values. I just made them up to make this example.
Okay.
And this is a standard example. The hawk dove game. This is also, by the way, there's another name for it. A game of chicken. You might have heard of that term. And the whole idea is to show there is one unique Nash equilibrium. Okay, so this is an example scenario where you have one unique Nash equilibrium. Again, this is another scenario where you have a unique Nash equilibrium. I hope that answers. I don't want to get details into this one. It's just something I made up.
Excuse me, sir. When the hawk is going to behave like a dove, hawk is getting the value of 5. and when the dove is behaving like a hawk, it is getting a value of 3. Why this discrimination in values? It should be almost equal. Or it is related to some probability function.
Could you repeat your question, please?
Sir, when the hawk is behaving like a dove.
Which hawk? Like which one? 1 or 2?
2.
Oh, blue or red, I mean.
Okay.
Typo here, both of them are labeled 2. They should be 1. Anyway, red or blue?
Red.
Okay. Okay, let's focus on the red. So?
When the hawk is behaving like a dove, the values are...
He's playing hawk. So the red agent is, his action is hawk.
Hawk.
Right? Okay. What about the other one? Do you want this person to be hawk or dove?
Hawk.
Okay, so both of them are hawk.
Okay.
So both of them are playing hawk. So their rewards are 3 and 3.
But when both the players are playing dove, the value should also be 3 and 3. Why we are having a different value? That is 5 and 5.
Why are they 5 and 5? I just made up those numbers, I said.
Okay.
That's all. There's nothing to it. It could be something else too.
Thank you, sir.
Okay.
Thank you, sir.
So, but I just wanted these two numbers, 3 and 3, to be less than 5 and 5. Because if both of them are playing hawk, then there will be a fight and they will incur some loss. So necessarily, this, whatever value I put here, I decide I could have made it 500. Then I could have made this 499 or just 1 or something between 1 and 499. Okay. So the actual numbers don't really matter. What matters is the relative worth. So these values are necessarily smaller than these values. Because when both of them are playing dove, the values of either agent is more because they are not fighting against one another. They are sharing equally. But when both of them are playing hawk as opposed to dove, if both of them are playing hawk, eventually the prey gets shared equally between the two, 5 and 5, but then you must reduce some amount because they incurred some, expended some energy during the fight. Okay, now here's yet another example. It's battle of the sexes. So we have a husband and wife. And this is an example where there's cooperation. The husband likes soccer, or in India we would say, we would have used cricket, right? So the husband loves cricket matches, and the wife likes to go to a star concert. Okay, now, again, there's no communication between them, mind you. No cell phone use or anything. So independently, they can decide. If both of them land up in the cricket match or soccer in this example, now both of them will gain something because the wife will gain the companionship of the husband, although she doesn't really like cricket. So the wife, W here is the wife, she'll get a worth of, the value is 3. But the husband not only enjoys the company of his wife, he also enjoys the cricket match, so the value is 3. 3 and 7. Okay. Conversely, if both of them go to the sitar concert, then the values instead of 7 and 3, switch them around, 3 and 7. Now the wife enjoys the concert more. On the other hand, if let's say both the husband goes to the cricket match and the wife goes to the concert, then the wife, since the wife, both of them are alone, right? The husband is in the soccer or cricket match, and so, but they don't enjoy one another's companionship. So he gets only a value of 2 because of the cricket game, and she separately from the concert she gets a value of 2. Now, if on the other hand, if the husband lands up in the concert, which he doesn't enjoy, and the wife lands up in the cricket match, which she doesn't enjoy either, the values are 0 and 0. Okay, so these are the values. Now here, what are the equilibrium? Here you can see that there are 2 equilibrium points. Pardon me? Lanavanda. I agree. Any married person would agree. Okay, so the point here is, unlike in the previous two examples, where here you had one Nash equilibrium, unique Nash equilibrium point, here you have two different Nash equilibrium points. So with equal probability under a fair scenario, which doesn't happen in real life, there's a 50% chance you land up here and a 50% chance you land up in the other situation. So anyway, this is a basic idea of Nash equilibrium. And now this is a well-known game of rock, paper, scissors. You know the game, children play this game of rock, paper, scissors, right? So each child can choose rock, paper, or scissors. Scissors cuts rock, so scissors wins over, scissors cuts paper. So scissors wins over paper. Rock blunts scissors, so rock wins over scissors. Paper wraps rock, so paper wins over rock, and so on. That's how the game goes. And so winner gets 1 and the loser gets -1. So if both of them play the same thing, paper, paper, 0, 0. It's a draw, right? Both of them play scissors, 0. And let's say this, the agent 2, the red agent, plays rock. And the first agent, the blue agent, plays scissors. Since rock wins over scissors, so the scissors, the blue gets -1, the red gets +1. Okay, so this is how we assign the values in this game. Now, in this game, the reason this is also a well-cited game, and by the way, a lot of papers, including in the top-notch journals, Science and Nature, publish rock, paper, scissors articles, including in the year 2014. It's a very widely studied research area. But the idea here is there is no Nash equilibrium. There is no equilibrium point. Just a small caveat, when I say there's no equilibrium point, I mean there's no pure Nash equilibrium. There is a separate concept called mixed Nash equilibrium, and there is in fact a mixed Nash equilibrium point. In fact, if you've heard of John Nash, the Nobel Prize winner, he got his Nobel Prize because he proved that every game under certain circumstances will have at least one mixed Nash equilibrium. But I'm not getting into what's mixed Nash equilibrium here. But as far as we are concerned for this talk, this is pure Nash equilibrium, and there is no pure Nash equilibrium in this game of rock, paper, scissors. Now, so here's a more general situation. Static games. We have n agents, also called players, and in this example, in the previous examples that we have seen, and in this example, there are only 2 agents, and each agent has a set of actions. In the other cases, both actions were the same, but that might not be true in all possible scenarios. For instance, in this game here, the first agent has 4 possible actions, A, B, C, D, and the other agent has completely different set of actions, P, Q, R, S, and T. And these are the values. Can anyone identify what's the best possible scenario here? 7 and 8, right? This person plays B and the other agent chooses Q. 7, 8, right? 7 plus 8 is 15. Nothing else gives you 15. The total value of both agents put together is 15 in this case. But unfortunately, this is not Nash equilibrium. What would be the Nash equilibrium here? One of the Nash equilibrium points is this one, 6, 4. Why is that? Because from 6, 4, remember that the left value pertains to this pair, and the right value pertains to this pair. So how much is the left agent or left pair getting from this? 6, right? But if this person who's playing D is getting 6 here, unilaterally changes to C, how much will he get? 4. If he switches to B, he'd get 3, and if he switches from D to A, he'd get 0. So for him, D is the best, right? Likewise, let's look at this player here, who's playing T. What is he getting? 4. The value is 4 for him once he's playing T. If he switches to S, he would get 0, which is less than 4. If he switches to R, he'd get 1. Q2 and P3. So again, this person, the second agent, does not have any incentive to move unilaterally. Okay, so this is one Nash equilibrium point. And the other Nash equilibrium point for this is 4 and 5. In fact, for this game, there are two Nash equilibria. Okay, and note that we are disallowing the case where both of them simultaneously change. That's not what we're looking at. Every possible sequence of actions we have to look at arbitrarily. So this and this are the two stable points. But this is actually the best for both. Okay, and so let's not go into this. I just wanted to give you an idea of Nash equilibrium. And now this is a project that I'm working on. What we have is a smart grid, and there's a power outage. What's it called in India? I forgot. Load shedding. Load shedding, right? So load shedding, for some reason, so there is I'm just used to power outage, so I'll just call it outage. Please don't mind. So there's a power outage, and now this is the isolated grid now. And discrete time intervals, 1 to uppercase T, that's the total number of time intervals for which the load shedding or the power outage will last. And each of them, the assumption is each of these houses is also equipped with a PV array. So they can generate solar power. Obviously, we're looking at the future. And so they can do several things. They can consume the entire power that each house is generating by running its own equipment, or they can sell some of the power, or if they really want to run something and they don't have enough power from their own solar array, then they can also buy power, right? And so here what happens is how many each of these households is considered to be one agent. Okay, and how will they adjust how much power will they sell or buy and how much will they consume? So we have modeled this. Now what happens is that we have considered two different kinds of loads. Fixed loads like lights are fixed load, fans are fixed loads. Air conditioning is fixed load. In other words, what happens is you need to run it at every particular time interval. On the other hand, another class of loads we call shiftable loads. Shiftable loads are like if you have an electric vehicle. And nowadays, electric vehicles are going to be sold. So you need to charge the electric vehicle. That's a shiftable load. You can schedule it for either time interval 1 or time interval 2 or time interval 3. So it's shiftable. It doesn't have to run throughout the power outage. Or not air conditioning, washing machine is a shiftable load because you can shift it either during time slot 1 or time slot 2 or time slot 3 or something. Okay, and so we have two different kinds of loads, and then what we do is how much satisfaction do you get from consuming the power? Okay, let's look at the fixed load. So this is the load demand, maximum demand for each time interval. Fixed load is LF, LF1, LF2, LFT up till LFT. This is the last time interval, after which power will be restored. Okay, this is the maximum demand. And then if you want to turn on all the lights, then that you get here, maximum demand. But we could do with only turning on few of these lights. And then the rest of the electricity that we obtain from our array, we can sell it, right? So what happens is we define a fraction alpha. Alpha is the fraction of the total demand that you are actually consuming. Okay, so the total power consumed is summation T equals 1 to uppercase T of alpha T LFT. LFT is the peak at each time slot, and alpha is the fraction that is actually consumed. Okay, and this is summed over all time steps. And I is the index of the agent. That's the total power consumed. Now, because we are operating the fixed load, we also get some satisfaction, some utility out of it, right? And let's say from full, if alpha is 1, that is we are turning on all the lights. Let's say that our satisfaction is 1. It's called the utility. It's 1. If I turn off 50% of these lights, what will happen? The utility will still be mostly satisfied, right? With 50% light, it's not like our utility will become half, it will become 0.7 of full or something. So we have a convex curve here. So alpha is 0 to 1, and the utility gained from that alpha is a convex function like this. And it's saturating towards 1. Okay, from 0 to 0.5, 0 is full darkness. From 0 light to 50% light, you get a lot of satisfaction, right? But from 50% light to 100% light, you get a little satisfaction. So it's basic economics, and that's why we have chosen a curve like this. So this is, by the way, summation of UFI of alpha I T LFIT, summed over all time instances. This is the total utility derived from the fixed load, summed over all possible time instances. And likewise, let me not get into it, but for the shiftable loads, sorry, this is a typo, these are shiftable loads. So shiftable loads, we have preferences. I want to turn on my washing machine during time interval 1, not time interval 2 or 3 or 4. So there are some desirabilities here, right? So the amount of utility we gain from operating each shiftable load also depends on which time interval it's scheduled. And so there is a formulation, let me not go into that. But just remember that we get a utility from scheduling the shiftable loads, and we get utility from the fixed loads. Furthermore, these are in, since it's a US project, these are in dollar terms, the monetary equivalent of the utility that we are getting. And then the rest of the power, so this is the total power surplus or deficit. So PV is the photovoltaic power that's been generated in each time interval, and this is the power consumed from using the fixed loads, and this term is the power consumed from using the from running the shiftable loads, and this is the total power generated from the solar array, and so this minus of these two will give you the total surplus power. It could be a deficit. If this and this exceeds, the sum of these two exceeds this, then this would be negative, in which case we have to buy power from some other source, right? Otherwise, if this is positive, we can sell power. And then we considered different scenarios. We considered without trade, and most, in all cases, by the it's very uncommon. Nobody uses individual generators. So we are looking at a scenario where there is no separate source of power like a battery or a generator that we can use. It's not part of our model. So with trade and without trade. With trade, we can buy and sell power freely. And without trade, whatever electricity we are generating from our own PV array, we have to use that. Okay, and so what happens is, the total utility from trade is how much when you do the trading, so we have selling price and buying price, and so the utility from the trade we formulated in this form, and the total utility from everything is the sum of the utility you get, how much money you gain from the trade, plus the monetary equivalent of operating the fixed loads, plus the equivalent of operating the shiftable loads. So this is the total value. And what will happen is, in the grid, each domestic household, that is, each agent, will individually try to maximize this. There is no coordination. What will happen is, eventually the system goes into Nash equilibrium. Okay, so Nash equilibrium, unfortunately, is not the best. And we got some results. I'll skip through this. So we have some preliminary results here. So this is what we get from just Nash equilibrium. And then we do some price adjustment to try to increase the utilities, total utilities of all the agents combined. And we were able to get something higher in each case by doing that. But at this point in time, what we are looking at is a multi-agent reinforcement learning algorithm. So the agents together will try to learn something so that they'll try to escape from the Nash equilibrium and get to another point which is best for everyone. So this is one application of multi-agent reinforcement learning. What I will do is, there are different algorithms for multi-agent reinforcement learning. Let me skip through all of them. The only thing I will tell you is that coordination is always required. Okay, this simple example, which I borrowed from a proceedings of the IEEE paper, this example will tell you how. Okay, now these are two robots, and they have both of them have to go to the goal state. This agent, in one time step, this can go from here, it can go north, and this Y can go left, right? And then in the next time step 2, this X can go from here to here, and Y, which is here, can go here. That is one possible way to do things here. So this guy takes this trajectory, this Y can take this trajectory. Alternately, this X can go this way, and this Y can go this way. That's another approach. Or they can both go this way and this way. Both of them go top, and then this person goes left, this goes right, and together reach the goal state. But if, consider the fourth approach, if X decides to go right and Y decides to go left, then there'll be collision, right? So they have to coordinate. It's not like you can individually train each robot to, oops. You cannot train each robot separately. They have to somehow, you have to coordinate the, train the robots to coordinate together. And so that's where you need multi-agent reinforcement learning. So let me skip all that. And of course, you guys are free to talk to me, chat over some masala chai outside or whatever later on. But there are several schemes for multi-agent reinforcement learning. It's a very state-of-the-art topic. There's a lot of research going on in multi-agent reinforcement learning at this point. Nevertheless, from the talks that I saw, many of you choose to use neural networks and radial basis function networks. And I thought that I'd spend 5 minutes giving you some ideas of, since I'm a machine learning person, my PhD back in 1994 was in neural networks, Hopfield neural networks, by the way. And subsequently, I've been working on neural networks for a long time. Neural networks today, it comes under scope of machine learning. So I prefer to call myself a person in machine learning area rather than a neural networks area, because neural networks is actually dead. So this is the timeline. Back in the 1980s, the research was on neural networks, LVQ, learning vector quantization, multi-layered perceptrons, which is MLP, neocognitron, cascade correlation algorithm, and so forth. These were the innovations from the 90s, 80s, and actually early 90s too. And the outcomes, and this is my perspective, of course, was this. Multi-layered perceptrons with just a single hidden layer is good enough. Input layer, hidden layer, output layer. And with m inputs and n outputs, 2m plus 1 is more than adequate for most real-world tasks. The training algorithm that's most effective is backpropagation. And you can use mean square error or a loss function like this, where you allow little tolerance without any penalty. this kind of loss function is more than adequate for practically all real-world applications. Moving on to the 1990s, we saw the advent of kernel-based methods like radial basis function neural networks. And radial basis function neural networks are also very popular. They work well with lower dimensional input spaces. And for higher dimensional, when the number of inputs is higher than 5, it's better to use multi-layer perceptrons because there's something called curse of dimensionality. You might have heard of the term. So RBF is not well equipped to deal with that. And for kernels with RBF networks, Gaussians work quite well for most real-world applications. Sometimes you might choose something more generalized, so you, instead of a just scalar variances, sigmas, you can have a diagonal covariance matrix. Only the diagonal elements are non-zero, in which case, if you've heard of Mahalanobis distance metric, anyway, so you're able to cover elliptical shapes like this, or if you have non-diagonal elements also acquire non-zero values, then you can, it becomes even more generalized. So the Gaussian shape can be of this form. It can be at any particular angle in the input space. Anyway, that's the 90s. Around the year 2000, again, this is all very rough. SVM started much earlier than that. So now what happens is, support vector machines received a lot of attention. Not backpropagation, multi-layer perceptrons, radial basis functions. So this is very commonly used, and then we have Bayesian networks, dynamic Bayesian networks, and so forth. But I don't do any work on these. I do a lot of work with support vector machines. And support vector machines are actually mathematically proven to be optimal classifiers. That is, for classification tasks, don't use backpropagation trained multi-layer perceptrons. Support vector machines is proven to be optimal. I'm not going to tell you what we mean by optimal, but this is the best approach. So if you are doing work with which requires classification and you intend to use neural networks, my advice would be go for support vector machines. There are a lot of free SVM classifier MATLAB code or C Java code available online too for your task. And you'll most likely get better results from that. Then moving on to the 2010s, deep learning is something that has received a lot of attention, and this decade is not over yet, and so deep learning is currently being used. Also, frankly, I'm not into deep learning since I'm also working on other research areas, quantum computing and game theory and all that. So I haven't focused that much on machine learning, but deep learning is something that's also that's looking very promising now. Outcomes, of course, is yet to be seen. Now, does it mean that we completely discard MLPs or RBFs? The answer is, are they still useful? The answer is yes. You can still use them. But this is my advice. If you are so used to classical neural networks, use them by all means. But don't use single neural networks. Use an ensemble of neural networks. Don't train a single neural network to do the task. Use multiple neural networks. Train them either with slightly different data or from, since you start with random weights, you can train them equivalently, but as long as they start with different random weights, they'll converge to different weights. And then, this is called ensemble learning, and there are some theoretical reasons why this will actually perform better than a single neural network. Now, there are two main classes of approaches here. Okay, this is the input space. Instead of one neural network, Okay, what I'm advising you guys to do is use multiple neural networks. 1 neural network 2 until neural network uppercase N. And then a simple situation where we just, the output, instead of taking the output of 1 neural network, take the average of them. What will happen is, if the error is epsilon for each neural network, then when you average them, the error becomes epsilon divided by square root of n, is the expected error. Okay, so you'll get more accurate regression from using multiple neural networks. Of course, this averaging is just a very rudimentary idea, but there are very sophisticated learning algorithms for this one. You use pseudo-inverse formula for here, and there's a very common algorithm called AdaBoost that you can apply. And this, so what will happen is, it works on multiple neural networks. So if you use AdaBoost, you train only 1 neural network, and then look at how much error. And then find out which of these, data points is giving the worst performance for this neural network. Train the next neural network using only those data, the one which the first neural network didn't perform so well. And so it's actually more detailed than this, but that's basically what this approach AdaBoost does. And this will give you a lot better performance in many applications than traditionally what you have used as a single neural network. The other approach is a mixture of experts. Now here, each input and boosting, the input is being applied to all neural networks, and all neural networks simultaneously produce their output, and then you're doing some kind of averaging here. By the way, if you're looking at classification task, okay, then you can, instead of averaging, you can use majority voting. Possibly, every neural network. Yes, you can do that. Yeah, you can use 100, all 100, you can train all of these. My advice is, what this AdaBoost does
idea is good.
What AdaBoost does is, the first one will be trained with all 100.
Okay.
And then
the same data to train data.
Different weights. So for each of those 100 points, you will apply different weights. The weights for which this one, for those points where this did not perform so well,
okay,
it gave higher error. Those will be given higher weights for the second neural network.
Okay, sir. Thank you.
And then you proceed like that.
Okay, sir.
Okay.
Thank you.
And every time you do it, you'll see that the error is going down and down.
This is
until it stabilizes. And this is a very simple approach, AdaBoost, and it will give you beautiful results.
Sir, one more question, please.
Yeah.
Sir, NN1, NN2 means two different types like MLP, RBFNN, or
well, it can be MLP and RBF also, but it can be the same
type,
same type of neural networks.
With different architecture or architecture?
Same architecture too is fine.
Okay.
But they're being trained differently.
Using different training algorithms?
No, using different weights of the inputs.
Okay.
Even the same training algorithm you can use on everything. You can use backpropagation on all of them.
Okay, sir.
Okay, and this will, I can guarantee you, this will most likely, not a guarantee, that's misnomer, but this will give you much better results.
Thank you, sir.
The other approach, mixture of experts, is now each of these neural networks is considered to be an expert in one particular domain. So what happens here is the total input space you group into different regions. And so this neural network is an expert in only this domain. This neural network is an expert in this domain, and so on. And then what happens is, so you have a switching device which will do, so this switching device receives the input also. And then it will decide which of this neural network is going to perform best. Okay, and it will decide which output to take, and then accordingly it will pick one of these outputs. I have some contribution in this one, and we have submitted a transaction paper, and hopefully it will get accepted pretty soon. I can share those ideas with you.
Hundred samples in the first case if we are done. If anyone is not succeed in its finding out the pattern recognition, we can eliminate them like BFO, and remaining one who are succeed can be taken over. That's how the iteration process will also be less, and we are getting a more successful results for getting a pattern recognition with very lesser time, I think so.
And what are you using once again?
What he is saying that in the first case, in NN1, if you are giving up the input, 100 samples, so whatever the errors are there, if anyone is finding out more error, you are saying that the weight factor should be increased. So instead of that, by weighting factor increased, if we are going for NN2, some other will be find out like that. Again, weighting factor will be increased. So every time 100 iterations you should be completed. Suppose there are n number of networks, so n into 100 times we have to do the iterations. Instead of that, which one would be succeeded will be kept over, like in BFO, and the remaining one which were not succeeded we will eliminate. So we will quickly recognize the patterns compared to this. So, am I correct?
First of all, I'm not a fan of using any of these stochastic algorithms in conjunction with neural network training because there are no local minima. You have
there are two things.
Quadratic error surfaces. If you have a quadratic surface, there is no local minima. You only have a single global minima. So in my opinion, it's not at all a good approach to use PSO or BFO or a generic algorithm here. Even if you use a more complex loss function, even then there is no local minima. What you in fact have is because of stochastic gradient descent, you might have valleys. Okay, which might give the perception of a local minimum, but it's not really a local minimum. So, now there will be error, and furthermore, what you are saying is, okay, if you have a population of neural networks, you pick the best one. Now, even then, this approach will perform better because if the neural networks, I'm assuming ideal training. All these networks have been trained ideally, maybe using BFO or something too, okay, in conjunction with backpropagation also. But even then, what will happen is, if the error, minimum error possible with BFO plus backprop or whatever is epsilon for each of these. If you simply take the average, the expected error will be epsilon over square root of n. It's a simple statistical observation.
Yes, sir, it's true, but more training epochs are needed for this.
More training epochs are needed, but then at the same time, if you're using BFO, you are also doing that, right? If you're training multiple neural networks.
Which will not succeed for finding out the food, we'll eliminate that one, we will take off of that one in the reproduction cycle, and we will again giving for swimming. So that's what I'm saying.
I see. But for most of these applications, the training time is absolutely not of any consideration. For all you know, even if you want to train for one whole day, that's fine. It doesn't affect. In some applications, how fast you converge is important. Yes. But for most applications that I've seen, that's of no consequence at all. In which case, you can afford any amount of training. Just don't overtrain, by the way. That's another thing. Okay. But this will work better. And like 3, 4, 5, 10. So these are the two approaches. And anyway, so in conclusion, well, whatever conclusion you can draw, there's a lot of theoretical research going on here, and LVQ is of current interest. I work a lot with, sorry, not LVQ, SVM, I meant, support vector machines. I've worked a lot with support vector machines and with ensemble learning. I work a lot with ensemble learning also for some applications, and there are a lot of scope for using some of these algorithms in your fields too. Thank you. So, any questions? Okay, so let's end the session. And
Sir, can you tell this reinforcement for any antenna applications?
I wish I could. I'm not an expert in antenna. Actually, I know very little about antennas, so that's up to you to explore. But I have been told that there are applications. My expertise in antenna is very limited. Yeah. In fact, just from the discussion during the brief break, tea break we had, one person discovered a application for reinforcement learning. But let me add a comment. You can just use basic optimization instead of reinforcement learning. Why do you use reinforcement learning in preference to optimization is because if you have an uncertain environment, if you have a dynamic or changing environment, you cannot do any optimization statically, and you need to learn while the neural network or whatever is being applied. If you need to learn it online, then you should apply reinforcement learning. Thank you.
Thank you, sir. So for the next session talk, I would like to invite for the session chair, Mr. Ernest Berger, who is a representative of FECO from South Africa. And the invitee talk will be given by Professor K.J. Vinoy on the topic of wireless power transfer in the age of Internet of Things. So Dr. K.J. Vinoy is an associate professor in the Department of Electrical Communication Engineering at the Indian Institute of Science, Bangalore. He received his PhD degree from the Pennsylvania State University, USA. His research areas include aspects of RF applications of microsystems and other topics in microwave engineering, including microwave antennas, microwave circuits, wireless power transfer, and metamaterials. He has published over 150 papers in technical journals and conferences. In addition, he has published 4 books in the areas of microsystems. He is also serving in the editorial boards of 3 journals and reviews submissions to several others. Dr. Vinoy is a fellow of the Indian National Academy of Engineering. So with the kind consent of the session chair, I would like to request Dr. K.J. Vinoy to please proceed with their presentation. Thank you.
I take for this talk here, and I sort of thought that I will talk on wireless power transfer for at least half a dozen reasons, and in the interest of time, I'm not going through all of them. But one important reason is that if you go through the papers that are read out in the last couple of days and probably today and tomorrow, a large fraction of these antenna papers that we see here are on antennas for WiMAX, WLAN, GSM, etc., etc. But we all know how many of them really end up being used for those applications. So rather than, presenting things like the cat drinking milk, proclaiming that our antennas are for this, so to speak, W for wireless, WXYZ applications, I thought I will talk about antennas plus some circuits that we could possibly build and use for some interesting applications that I will talk shortly. Internet of Things, or in short, IoT, is something that is relatively new. I started hearing about it in maybe about last couple of years. So what it is all about? It refers to, some scheme with which we could construct an internet-like configuration to identify and communicate between various objects or people. When we look at it, when we look at connectivity from the ICT perspective, communications, what we are trying to do is essentially connect this anytime, any place, with anyone. And as we move towards IoT, we add one more A to that list to try to do with anything, any object. So it is essentially a foundation for connecting various things. It could be in terms of, maybe this may include sensors, actuators, and many other smart technologies. And the main emphasis there is, as I understand it, is coming from the radio frequency identification technologies, RFID technologies, where that's one of the let's say most widespread identification technology that is available today. So the question is how we could extend the RFID approach to some of the other things that you see in the paragraph above. Although we started hearing about it in the last 1 or 2 years, there have been several efforts on those directions, and I'll skip in the interest of time. And this has multiple applications that are projected in transportation, to healthcare, for example, medical sensors, to smart environments of various kinds, in terms of deploying sensors and various other things to work and network them to work in a cohesive way to personnel and other applications. And as I said, these work primarily from the from an RFID system point of view. There are several interesting differences between how an RFID system would work compared to a conventional communication system. In a conventional communication system, we will have the we will have the local oscillator which will basically modulate the baseband and then communicate through the channel, and on the other end as well we will have something similar. And when we try to have hundreds or millions of tags, that approach will not work. So what is normally done in the case of RFID tags is that most of the communication building blocks are basically built into what is called a reader, and in the tag there is very little hardware deployed. And in fact, the way it is done is that we have two different types of ID tags, and the most popular one is the passive tags, in which there is no real power source inside the ID tag, and that's why we could use it. We could produce and use them in large numbers, and there, what is the reader does the job of providing the local oscillator signal into the stack, and so that it can, what is called, it can use what is called the backscatter communication to send back the information into the reader. There are also active tags which may have batteries or some other kind of storage, in which it could also be possible to have such, some amount of processing, including local oscillator generation being done. But they, because of the complexity involved and the power requirements, they are used in extremely few, very few situations that you would see. And I guess most of you are familiar with the system, RFID system. It has a reader unit interfaced to a computer, which has an antenna that basically sends out the local oscillator as well as this other interrogation signal. And at the tag, which, as I said, is effectively a passive unit, it backscatters this information, and from there it makes sense out of those backscatter information to identify the tag there. And it has huge number of applications here on the key for your room also is a RFID based network one. So there are a large number of applications across the world. Now, how do we extend it towards what is called this Internet of Things? RFID, as I began with, is a prerequisite. It has the transmission, radio waves. It has the radio wave transmission into it, which is essentially used for the backscatter with which the identification is done. It's proven across the world. You can have millions of tags, and these could be identified uniquely, and it is proven to be a very cost-effective system. They are extremely cheap, at least in a global sense, at least compared to a full-fledged communication transceiver system. And these tags are more or less interoperable. There are a couple of standards available with which, if you operate with them, you can have tags from one manufacturer being read by a reader of another manufacturer to a good extent. They are not completely compatible, but at least you can have a reasonable setup made which would work independent of the manufacturer for these tags. But one very important aspect is that most of these tags are passive. That means they do not have any batteries or storage mechanism inside them. An evolving modification is that we can integrate some sensors into this. Various approaches have been looked at, but the related aspect is that sensors usually would require a power source. So we cannot continue to stay on the realm of completely passive tags. We need to somehow have energy in them, and maybe try to utilize the communication as it is done in a RFID tag to pass back the information from the sensor. So the idea essentially is that if we can have generate or accumulate or store energy in these stacks to at least work for to provide to at least to operate the sensor, so that we can deploy them incorporating all those features of a typical RFID tag. There was a platform made at the University of Washington by a joint research with ITL a few years back, where they tried to harvest the ambient RF energy and then use that to do the sensing and then interface it with the RFID platforms to do the communication. And if you look at the commercial scenario, there are several RFID sensors available in the market. Many of them work, with some kind of energy harvesting scheme. One of them is by Overcast, which we looked at very closely, and it actually harvests the RF energy at reasonable power levels. We'll maybe talk about it a little later. It tries to harvest one of the suggestions from them is to basically try to harvest the GSM, which is at about 900 megahertz in India, and because there is some power available. Again, this is a suggestion because the power levels required to operate these devices is somewhat higher than what you normally face in an typical ambient scenario. And this particular system works to as low as -12 dBm, and they claim that it has efficiency all the way up to 40%, but not at -12 dBm. It is when it is at much higher power levels. And they have different modifications to it, and there are multiple other commercial suppliers for similar products which will work on a harvesting scheme. So if you look at the state of the art in this particular domain, there are several different variables being sensed, which includes most of the environmental variables. And these are integrated with the ICs, and sometimes these are with MEMS-based sensors. And the products that are available, on the other hand, all of them work on RF energy harvesting. But although we say RF energy harvesting, as I said a little while ago, the power required to operate these are so high that you don't normally have such amount of power available easily in the ambient. So in effect, to make this work, you basically need to intentionally generate the RF power at sufficiently high energy density so that these could work. So in effect, the energy requirements for the sensors or the wireless module is the bottleneck for the widespread use. Otherwise, we could just have a very simple antenna attached to a small battery or something, and that can make things work. So if you really look at the power requirements for a typical wireless sensor network modes, what they call it, there are several of them available. One comparison is shown here, and if you look at it, you need currents in the order of milliamperes at about 3 volts to make this work. That would basically translate to some milliwatts to make this work. But the good thing is that they are not in the communication mode all the time. if you have a scheme with which you accumulate energy, sufficient energy, and then communicate for a few milliseconds, for example, that may suffice in most applications. And if you look at what is really available in the form of chips, not necessarily as boards or packaged products, the situation is also somewhat similar, and we have looked at various options, including what is called the Bluetooth Low Energy for this purpose, and we still would need the during the transmission cycle, we will still need power in the order of milliwatts. But there are other different metrics with which you could compare some of these. And what really matters is that to enable one full cycle of communication in terms of making the sending out the handshake signal with this with a, let's say, reader or any other destination, and then passing out the packet of data. So if you look at them, there is significant differences between some of these chips that are currently available and the standards that are used. So to have this power of the order of milliwatts, let's say, you have multiple options. And then what could be the best option? If you actually compare what is used in a typical watch, for example, it works. There are watches, we have been using watches which were like key wound, or there are watches which work without even key winding. We used to have these automatic watches, which accumulates the energy in terms of all those mechanical motion. There are watches which work based on the solar energy. There are watches even which work based on the temperature on your body, and there are I think I have a picture of that. There is one Seeker watch which just scavenges based on the temperature on your body. So all those options are available, and then what's the difference? The difference is in terms of the energy, the power requirement of operation of all these. You have for a wristwatch is of the order of microwatts, whereas some of these sensors are of the order of micro to milliwatts, and a typical wireless mode will be of the order of into milliwatts. So there is a huge difference in terms of the power requirements between these. Now, what are apart from the ones that I just mentioned, what are the other options? There are several options being tried out, and people have been evaluated in terms of what's the energy density available per unit area. And the solar PV is the most popular with a very high energy density, and there are several others, including mechanical motion, vibration, and the like, which could possibly be used in the context of harvesting energy. And if you look at it, the ambient RF, although it is very low as you see in the list, is another source of energy. But if you really look at it, all these forms of energy harvesting would require some kind of ambience in which you have either these available de facto. For example, in an aircraft or in an automobile, the vibration will be available, whereas possibly if it is a body-worn device, you don't have vibration available. So it's essentially decided based on the deployment scenario. On the other hand, RF, as we know, is now available almost across the locations where people live. Now there are mobile phones and there are mobile towers. So that's something that we can possibly depend on. Of course, light is also something that is available. So we can make a mix and match between these various sources of energy. There is a possibility that we can have a consistent supply of the power required to work on these devices. So these are some of the schemes that are used for harvesting. I don't get into the details of it. One possibility is that we can use solar, and as I mentioned earlier, we can have substantial, power availability out of these schemes, especially when you are in outdoors. But there are some situations unique. For example, at night you don't get, and maybe if you are inside a confined environment where there is no light, then also there are problems. So we had a couple of such situations in mind, and therefore we started looking at RF as the possible scenario, possible way of harvesting the energy. And when we look at RF, we compare the demand and the supply available. The power, we need power essentially to do the sensing as well as for the communication. But luckily the peak currents are required only during this thing. During the communication, and therefore if we have some scheme for buffering the energy, which could be done with multiple ways using any type of rechargeable batteries, including a thin film battery that I'll show in the next slide. So these are some of these options for storing energy. We have this now widely popular lithium-ion batteries. There are thin film batteries which have much smaller energy density, and there is also something called supercapacitors, which could be charged very quickly and can be used, much more number of charge-recharge cycles. If you compare them, and considering that we only need milliwatts of power, and they probably need to work only for few, transmission cycles. There are, these options would appear sufficient, and therefore, lightweight and all those special advantages. And some of these could even be integrated with integrated circuits. Another reason for probably considering RF would be that the RF, we could harvest the RF either coming from the ambient sources, which could be GSM or this WiMAX or some of the others. We also can have exclusive sources such as an RFID reader, which could basically pump out the energy to energize these harvesters. These are some of the listing of the ambient RF sources that have been looked at. For example, Wi-Fi access points. You have these 2.4 gigahertz access points across, buildings. Cellular towers with various, the frequent 900 megahertz bands and somewhat 1800, almost anywhere in the country. TV broadcast is there, and a couple of other interesting options. It could even be FM broadcast. Most of your mobiles will receive this FM. There are also AM broadcast, which is the all type. And interestingly, the power that these have, some of these have very high power transmitters, and therefore there is a possibility that we could, work with some of these schemes to harvest the energy. And the one of the interesting, apart from these higher power levels, these lower frequency ones also work on no line of sight, and therefore you can harvest even if you are not in the close vicinity of the transmitter. Of course, the power availability would vary from place to place, and it is also possible that the practical scenario would be something that is you actually intentionally generate. And when you say it is intentionally generated, you are basically coming to the realm of what is called wireless power transfer. You have a RF source which is intentionally generated. It is placed exclusively for the purpose of energizing your device. The wireless power transfer, incidentally, is not something that is happened over the last 10 years or something. It has been there for more than 100 years. Tesla had done some experiments, and in 1960s, somebody by name Brown has actually demonstrated that you can even fly a helicopter by beaming the RF into it. He has actually flown, I understand, for about 10 hours, the helicopter, by using this RF energy. What it essentially has is an antenna coupled to a rectifier. And he, in fact, coined this term called rectanna, which is this combination of those two. There have been a lot of emphasis on trying to do this, what is called space solar power station, wherein in the night, when you don't have light on ground, you can probably have a satellite sitting at the geosynchronous orbit, which would collect the solar radiations and then convert them to microwave and beam it down to the earth. There was some mention of it yesterday. But when we look at this large distance power transfer, there are several bottlenecks. The power generation, there is a finite efficiency. The antennas have finite gains. And you also have what is called the free space loss factor. And to put this into some kind of numbers, if you forget everything else, just look at the free space loss factor at 1 gigahertz, closer to GSM, which is at 900. The wavelength is 30 centimeters, and at a distance of 1 meter, the loss factor is 0.07. So only 7% of energy transfer would happen if you have antennas, at 1 meter separation. There are several other issues with respect to the, large distance power transfer. But interestingly, there are some possibilities in which we could actually use the large distance power transfer. For example, if you have a mine shaft or a tunnel through which you could actually do, like in a waveguide situation. We have been also working at power transfer within a cavity. If you have a transmitter sitting somewhere in a cavity and it's like a large, even if it's a large metal cavity, you could have this wave rays getting bounced here and there, and finally, obviously, reaching your destination. So I could have a very high efficiency of transfer through the space in between. We had a project on from Boeing to work on that. There are other possible ways we can look at possibly surface waves, some kind of a focusing scheme, or can have, sometimes there is a possibility to have a high Q cavities to artificially boost up the energy available for rectification. In terms of shorter distances, many of you would have seen a few years back, there was a demonstration of wireless power transfer over, let's say tens of centimeters by a team from MIT, which has basically excited this area of wireless power transfer. In fact, there are industry standards with which, you may also have seen phone chargers, Nokia phone charger, which will work at, which essentially works at 100 kilohertz or something like that. And, there are solutions available. So if you compare these two, I was just thinking about that, several interesting extremities, this works in the order of milliwatts, the phone charger, whereas the wireless power transfer is the scheme in which you basically look at transfer distances of the order of millimeters in the phone charger, whereas on the other end, it is in the order of, it's in the geosynchronous orbit, therefore, thousands of kilometers apart. In terms of frequency, or in terms of size, or even in terms of the applications, let's say, because this is already a commercial thing, whereas this is still a blue sky research primarily driven by Japanese agencies. So in wireless point transfer, the key is that you have an antenna and a rectifier. So the design of that as a joint system is what really makes it, determines the efficiency of the system. So you have an antenna, which we normally design an antenna for 50 ohms as the input impedance. We have a diode, and we have a load, which is, let's say, think about a capacitor, which is a reactive. So what we need is essentially an impedance matching scheme in between these two, which would transform the antenna impedance to what you see on the other side. And that is one of the major challenges in the overall design of a rectangle or the rectifying circuits. But there is some interesting aspect to it too. For example, when we try to make a matching circuit, which by intention is a reactive network, and when we have a reactive network, there is a quality factor associated with it, and if we can design it properly, the quality factor of this circuit would boost or magnify the incoming voltage here. Why is it important? Because a diode will have a threshold voltage. If your input is in the order of microvolts, it doesn't really turn on the diode, and therefore nothing will go to the other side of the load. To make it to go across the diode, to cross the cut-in voltage threshold of the diode, we basically need to somehow boost up the voltage. So the quality factor of this matching network therefore plays an important role in doing an efficient energy transfer from an antenna to this rectifying diode. There are several schemes of implementing these rectifying diodes, including some of the new generation techniques in terms of fabrication technologies. And typically what you see is that the best that are reported in the literature, if you see, when you have power in the order of watts, you can get efficiencies, good efficiencies. Whereas when you have power in the order of microwatts applied, your efficiency is so low. So if you have 10 microwatt coming and the efficiency is 10%, you're only getting 1 microwatt on the other side to the in the storage by itself. So there is a huge challenge in when we are operating these diodes to harvest the energy out of the space. So if you just summarize what we have seen the scenario, the RF is one of the options to do the harvesting, and the effort on the other end should be to get the voltage in the order of, the power supply in the order of few volts, and when required in the order of milliamps of current. So to do that, it is not just sufficient to rectify and keep it with you. You may have to do much more than that to generate the voltages and currents on the other side, and achieving these with the maximum possible efficiency is the key thing. So let's look at what we have done in that context. I worked with one of my colleagues by name Dr. Prabhakar and several students over the last 5 years or so. And these are all MTech students, by the way, they are not PhD students. And I had some funding from a consortium called Aerospace Network Research Consortium. And also recently there is some interest, there's a small funding coming from RICO Research to look at this particular topic. So the circuit that the first batch of students did was essentially like this. The rectifier block of it is like this. You have the RF coming in from the antenna, and you have the diode, and this essentially forms the high Q, I mean the Q, whatever Q that you can get, the with the matching network with the quality factor that is. And a small capacitor is put there and the other side is the rectified output. If you look at it at 950 megahertz, that's actually the downlink frequency here. We can get reasonable, let's say voltages in the order of millivolts. For power, if you see, all the way from this is 10 microwatt to 100 microwatt. And the evaluated efficiencies are here. So, you could use tools like ADS and then get the efficiency curves based on the, the equivalent circuit of the diode, at the operational power and frequency, and, evaluate the best efficiency point and make it to work. As far as antennas go, we have looked at several antenna configurations. If you can see it, this is a biquad antenna, which is like a diamond-shaped wire placed in front of a ground plane, which has a reasonably high gain of about 10. And this is a patch antenna that our group has been working on. This is a planar inverted F antenna for specific reasons. And the overall scheme looks somewhat like this. You have this tuned rectifier I just showed you, and whatever coming from the antenna is stored in what is called a supercapacitor, because it can take tens of thousands of storage cycles. And then we have a series of circuit which essentially decides when to activate the microcontroller which will do the communication later. So I don't want to get into the details of it. We did a lab experiment. They built the hardware, as you see here. This is RF in, and this is the antenna that is used for the communication later, not for the harvesting. And we transmitted signal because inside the lab we need to have the constant power supply so that we can evaluate the performance of all the circuit that is generated. And in the end, this antenna here will communicate to another, let's say, Zigbee module on a laptop. This is a lab experiment. We tried with some of those different antennas with different distances, and the metric here was actually, how long does it take to accumulate sufficient energy to do communication across. We use the internal temperature reading of the chip as the packet that we transmitted. And as you could see, as the distance from the RF power transmitter to the receiving antenna increases, the availability will become less, and therefore the time to transmit will also increase. We actually did experiments outdoors with a tower which is about 200 meters away, and could get voltage across the capacitor that could be, the storage devices that could be used for this. There was a number of innovations in the circuit design that was there outside the scope of this audience here, so I just list them and move over to probably the efficiency calculations. As you see here, because we basically need to cross the diode, and to do that we need to go above the threshold voltage of the diode, and therefore depending on the input power levels the efficiency could vary, and that's the efficiency when you do on the other side of the diode by itself. And if you look at the complete circuit, including what you store, what you accumulate over a long period of time and communicate in once in several minutes, and look at the calculation, it is of the order of few percent. We had also tried to integrate multiple sources of energy with another set of students on what is called a universal energy harvesting platform. We had sources such as RF, solar, thermoelectric, and the like. And individually evaluated some of those. For example, when we look at the RF circuit harvesting part, as before, the efficiency could vary between 20% to 60% depending on the RF input power. But interestingly, the duty cycle, which is the time to transmit, with, for example, an RF power level of -7 dBm, which is, as you see, 20 seconds, is comparable to what will happen in indoor, where you can have a light intensity of the order of 200 lux. So it's not too bad indoors compared to what a typical PV harvesting scheme that is available. Apart from the GSM or LAN kind of schemes, it's also possible to harvest out of FM radio signals, which is again available across locations. To really look at the spectrum, there is substantial field density available at the FM bands. I guess it is true almost everywhere. This was a picture from a paper published from I think Georgia Tech, and we looked at it ourselves. This is what happens in let's say my own office room. We can get of the order of -20 dBm with a custom antenna, which I'll just show. So there is substantial power available even in some of those bands. In fact, I had a couple of students working on this just as a class project. They built a small antenna, monopole type antenna, which is a meander line, and made it to work at around 95 megahertz, and use that to harvest the energy. This is the voltage multiplier that we use, and this is a work in progress. And this is, at the moment, the rectifier part is just the simulation. So, we are working on this hardware to build, to harvest the FM band as well. If we really look at the use scenarios, as I said, there was a project from Boeing to work on this RF harvesting for RFID sensors. The interesting application that they had was to use this for sensing the fuel levels in the fuel tank. So the idea was to have a transmitter sitting somewhere inside the tank, and the tank is obviously metal, so the energy from the transmitter will not go anywhere else, and this could be collected by the a harvesting unit, which is essentially sitting along with the sensor. So basically the objectives were to build the unit so that it works almost, it has size almost similar to a typical RFID board and sensors that they use. So our job in this particular context was to build an antenna that is what the PIFA antenna that I had mentioned earlier. This has the patch here. There is a shorting pin, or rather shorting strip, and this is the feed point that you see here. I don't want to get into the details of it. Here is the experiment that they did inside a closed enclosure at Boeing, and I guess you could see the antenna here in a box. This was, I think I presented this in the last AEMC. The box was designed so that the fuel does not come in contact with the antenna per se, and they have done communication using power harvested using this approach. As I mentioned, it is also possible to work at much lower frequencies and do a coupled power transfer. A coupled power transfer is almost like the transformer principle, except that rather than having the fields confined using magnetic lines confined using the metal core, here it will be like an air core transformer. So there are, as I said, there are also standards available on that with what's called, they call it, I think, Qi. What is done is that you have this coupling coil, and on the other side it will be rectifying as we do before, and voltage conditioning to operate the device. On this side, you have the AC coming in, which will drive based on the load that is available. So we are working on a scheme to do the power transfer to energize some interesting wireless power devices. So that's another approach that could be. So what I wanted to say over this lecture was to, just deflect the attention from the conventional wireless communication point of view into, maybe power transfer, and you could look at, as I said, all those wireless bands, multiple wireless bands, or any one of them, or multiple of them, and you could also work with possibly, different schemes incorporated along with the wireless to maybe operate another wireless device. So there is enough fodder there to scavenge on, to look at new schemes, and this is something that, as I said, we have done it using master's students, and I'm sure you're on, those, at least for those younger faculty around here, you will find that tens of students will be excited to work on some such things where they can actually build hardware. Unfortunately, in India, we find that students interested in building hardware is, significantly depleting these days. So I'm sure your own students will find it exciting enough to look at some of those topics. So that's the main point, and I think I have not taken too much of your time for your own lunches. As I was telling Professor Guha, I myself was hungry, so I basically tried to run through a little bit, but I hope I have conveyed the message that I wanted to make today. Thank you. Any questions? I'll be glad to answer them. And if you're too hungry, we can talk over lunch.
Something like a comment. Thought of harvesting energy from the leakage in the high power transmission line. There's so much of leakage. I mean, the power companies consider around 35% transmission loss. So maybe we can harvest power from the leakage and somebody may sell it back to the power company itself. Or, I don't know. Have you ever thought of that?
No, I didn't think about it, but it's possible. But we'll have to see how, so far we have worked in the I have gone only down to megahertz. Now you're saying going to hertz. I'm not sure. We can see how best we can do that.
I'm also not sure. Actually, I am also working like some to this 1 gigahertz range up to the for power harvesting. But just an idea that is possible because that's huge leakage of energy. How is it related to an antenna gain?
Now, first of all, antenna gain comes into picture when you are. No, I was going to say something slightly different. The entire scheme here is based on the efficiency. Rather than the direct the gain per se, it's actually the efficiency that really matters here. So, if we can have a scheme, because in power transmission that he said, it is 60 hertz. It's not 61 hertz, 50 hertz. It's not 51 hertz, it is not 49 hertz. So we can possibly have an extremely high Q scheme, which could basically, let's say, couple energy and can make it to work. I don't know. It's possible.
Can be a challenging problem. That's what I feel.
Challenge to everybody. Yes.
Excuse me, Mike.
Young researchers are facing problem for the maintaining of cell phone because of you're busy with busy cell phones. Can you implement this wireless power transfer to our cell phone?
Wireless power transfer for the phone?
Phone.
Okay.
Is it possible? My idea is there because of researchers are young, researchers students are busy with only phone. Even though I am not objecting, but they are busy with all multiple activities. I am appreciating.
Not just researchers, everybody is.
Everybody.
So
I've got the idea of is implementing or not. Yes, sir.
Well, I think I have seen several people looking at this particular issue.
Okay, sir.
I suppose what you mean to say is that, let's say, harvesting the energy as we move, not just wireless power transfer. So, in fact, on the other side, first I'll tell the other side, which is you are radiating out so much power that it's of the order of hundreds of milliwatts. You could harvest out of the power that is going out from your phone. We've actually tried to do that. Your phone radiates in hundreds of milliwatts. So if you have a harvester sitting next to the phone, for example, this, you can harvest out of the phone itself.
Oh, that's right.
Okay. So we are trying to look at that particular stuff. It's also possible, as you said, the phone, when it is not being used, you already have a 900 megahertz antenna there. It's possible that you can probably take it out and scavenge it over a long period of time. But having said that, the requirement, the energy requirement for a phone is much higher than the numbers that even I talked about. The energy density, the energy stored in a battery in the phone is so high that you probably store over a day and use it for half a second, and that's not sufficient for a voice transmission. For a data transmission, in some contexts it might be sufficient, but voice transmission you need it for seconds at least. You need it for minutes at least.
Thank you.
Every people is having of the mobile, and every is having of the problem encountered that they are not having sufficient power in their battery, in their mobile. Every time they are in search of plugins. So instead of that, if we will use this simple circuit of power harvesting, taking up the output power of the same mobile, given to a rectifier, impedance matching, and the output power is again fed back to the same antenna, the battery discharge will be reduced or not?
How will it happen? You have to generate the output power you are spending, and then you are collecting. No power transfer scheme is 100%. There is always dissipation at the source.
But some of the power may be utilized, right?
That was only a very small fraction.
But in the emergency cases, it may be useful somewhat.
I don't know, because again, you need to accumulate it over a long period of time. So I don't think you will be. It will make, let's say, economic sense to do such a thing. Well, I don't think.
Okay.
Okay. Thank you. I hope to see at least one, wireless power transfer or harvesting paper at the next IAW. Thank you.
Excuse me. Thank you, Professor Vinoy. I trust we have all been inspired to go and research wireless power transfer over the next year, and I'm confident we will see papers on both the receiving and transmitting ends at Indian Antenna Week 2015.
Thank you, sir. So I thank our session chair, Mr. Ernest Berger, for chairing this session, and I also thank Mr. Professor Vinoy for delivering such a nice and informative talk. Now we will have a break for half an hour break for lunch. So now for the research paper presentations S3 session, we will be assembling here sharply by 2 p.m. 2:15 p.m. Thank you.